If you've watched the last two lessons, then hopefully you have a fairly strong grasp of how to write electron configurations. In this lesson, we're going to continue that and build on this idea of how electrons are configured. Now, all these electron configurations that we've been writing in the last few lessons have basically been what we call ground state electron configurations. Now, what that means is that ground state electron configurations are the most stable electron configuration for an element. And atoms spend most of their time in the ground state. So for example, on a test or on a quiz, if it says to write the ground state electron configuration for an element, well, that's basically asking you to write the regular electron configuration. That's what you've been learning to write for all of these lessons so far. That's kind of like the electron's home. That's where they spend almost all of their time. Well, sometimes those electrons aren't always going to stay at home. Sometimes they go on vacation, if you will. Sometimes they move around. And just like when you go on vacation and you get excited, well, when these electrons go on vacation, they get excited as well. And so they enter what's called this excited state. And that's what happens when energy is added to an electron. And it causes that electron to jump to an outer energy level. So let's draw a picture of that and see if we can figure out what's happening there. Let me bring the pen up here. And we'll take the example of an atom. Here's a nucleus, and we have, let's say, an atom that has a few different energy levels here. And there is an electron right in, let's say it is in the second energy level right there, and that's its ground state. And we add energy to that electron, perhaps by means of adding electricity or adding heat in a flame, something like that. Well, that causes the electron to jump to an outer energy level. And by the way, when that happens, that jump is called a quantum leap. So after it's undergone this quantum leap, well, that electron is all excited. It's in this excited state. Now, that excited state can't really last very long because eventually that electron has to go home. It can't stay on vacation forever. So the electron has to go back to the ground state, and when it does that, it gives off energy. You know, energy was added to that electron to make it jump out. Well, that energy is released when it jumps back to its ground state. And that energy that is released when it jumps from the excited state to the ground state is light. And normally it is light in a very specific wavelength or color. In fact, we find that every element, when it undergoes this process, it emits light in a very specific wavelength, a very specific color. In fact, we can identify elements based upon what color light they emit when this process happens. That's an entire topic in chemistry called spectroscopy. Well, let's take a look at the element aluminum. So we can see where aluminum is on the periodic table right there. And if we look at its electron configuration, hopefully by this time you realize that it's 1s2, 2s2, 2p6, 3s2, 3p1. So that's its electron configuration. Now, what does this mean? Well, if we look at its electron configuration, this actually is like a map telling us where the electrons are. So, for example, this coefficient of 1 out in front here tells us that those two electrons right there are in the first energy level. And then, if we want to look at the second energy level, then these 2's out in front represent the second energy level. So we have 2 plus 6, which is 8. So in the second energy level, we have 8 electrons. And then we can look at the third energy level. So the 3's out in front here represent the third energy level. So 2 plus 1, we have 3 electrons in that third energy level. And so based upon the electron configurations, we can actually decide or determine where the electrons are. Now, of all these electrons, really the most important ones that we're concerned with in chemistry are the ones in the last, the outermost energy level. So in that case, that would be these 3 electrons in that outermost energy level. In fact, those electrons are so important, we give them a name. We call those valence electrons. And valence electrons are the electrons located in the outermost energy level of an atom. And those are important because those are the only ones that participate in chemical reactions. So anytime you see an explosion, or food is digesting, or grass is growing, anytime there's a chemical reaction taking place, it's the valence electrons that are actually doing the chemistry there. So let's try an example here of the case of boron. There's the periodic table. We can see its electron configuration is 1s2, 2s2, 2p1. So based upon its electron configuration, we can find the outermost energy level, which seems to be the second one. And so 2 plus 1 there, that tells us that boron has 3 valence electrons. So we can determine them pretty simply. Well, how about gallium? That would be this element right here. Well, its electron configuration is a little bit longer. It's something like that. Can you determine how many valence electrons are in that atom? Well, hopefully you see that the outermost energy level this time is the 4th one. That's the highest coefficient. So 2 plus 1, that's 3. So we have 3 valence electrons. Now that's interesting because you might remember that we've looked at 3 elements here. And we said that the boron right there, and aluminum right there, and gallium all have 3 valence electrons. And they're all in the same group on the periodic table, which happens to be group 13. Now, I wonder, is that a coincidence or is that a pattern? Well, let's try another group on the periodic table and see if something similar happens. Let's try fluorine this time. Now, if you look at the periodic table, there's fluorine, and there's its electron configuration. Can you see that it has how many valence electrons? It has 7 valence electrons. And how about chlorine, the element right underneath it there? Here's its electron configuration. How many valence electrons does chlorine have? Well, sure enough, it's 2 plus 5, so it has 7 valence electrons. So it seems like all these elements in group 17 seem to have 7 valence electrons. And so there's a pattern there too. In fact, we could do this for the entire periodic table. Now, time doesn't allow that, but let's look at the grouping here. All the elements in group 1 will have 1 valence electron. So that would be all these right here. They have 1. If you look at the next group over, group 2, they all have 2 valence electrons. If you want to look at group 13, those have 3 valence electrons. Group 14, those have 4. And so you can see that there's a pattern here. It seems to be pretty predictable. How many electrons or valence electrons do you think are in group 15? That would be 5. Group 16 elements have 6 valence electrons. Group 17 electrons, like we just said a minute ago, have 7 valence electrons. And group 18 elements, the noble gases, except for helium, have 8 valence electrons. So there's a pattern here. In fact, what some students like to do is they actually write this on top of their personal copies of the periodic table. They write 1 valence electron on top of group 1. They write 2 valence electrons on top of group 2. And they do the same thing on the rest of the periodic table. 3 and 4, 5, 6, 7, and 8. So they know how many valence electrons are in each group. Now, we didn't mention the ones in the middle. Most of those transition metals actually have 2 valence electrons. There are a few exceptions, as you can see, but generally speaking, those transition metals have 2. Now, this is important because there is a very important state for elements. Now, of all these valence electrons, there's actually one state that's very important. We'll talk about that in a second here, but let's get some practice. How many valence electrons does arsenic have? Well, I hope you realize it's in group 15. It has 5. How about calcium, this element right here? Do you see it's in group 2? So it has 2 valence electrons. How about the number of valence electrons in thallium, this element right here? Well, it's in group 13, so it should have 3. All right, now back to what I was talking about a second ago. Oh, there's one more. Krypton. It's in group 18, so how many does it have? It has 8. All right, now back to what I was talking about a minute ago. I got ahead of myself. There's a very special state when it comes to valence electrons. It's called an octet. And of all these states, of all these numbers of valence electrons that an atom could have, the octet, or having 8 valence electrons, is really the most special. And that's because atoms are most stable when they have an octet. And so that means that atoms that don't have an octet are going to do things in order to get an octet. So sometimes they will gain electrons, they may lose electrons. Who knows what they'll do? They'll do all kinds of things to get that octet. Let me show you what I'm talking about. Let's say we have fluorine here, and we can see where fluorine is on the periodic table. And we know it has 7 valence electrons. So it has 7. It would really like to have 8, that octet. And so it's going to do that by gaining 1 electron. And when it gains that electron, it's going to get a negative charge. And so it's not going to be just plain old F anymore. It's going to be F negative. Now, why is it negative? Well, because electrons have negative charges. And so when you gain 1 electron, what you're gaining is a negative charge. In fact, we find that all of these elements here in group 17 that have 7 valence electrons are going to do the same thing. They're going to gain 1 electron and have that negative charge. Now let's try another example. Let's try oxygen right here. How many valence electrons does oxygen have? Well, it's in group 16, so it has 6. It would really like to have 8. So how is it going to obtain that octet? Well, it's going to gain 2 electrons. And so when it has an octet, what's its charge going to be after it gains 2 electrons? Well, it's not -1, it's -2. And so it's going to look like this. It's going to have that 2 negative charge in front of it. In fact, all these elements in group 16, like sulfur and selenium, are going to do the same thing. The ones that are nonmetals, they're going to have that -2 charge. How about nitrogen right next to it? We see where nitrogen is. It has 5 valence electrons, but it would really love to have 8. So what's it going to do? It's going to gain how many electrons? Well, it'll gain 3 electrons. And so when it does that, what kind of a charge will it have now? It should have a -3 charge. So we're going to write its symbol like that. And so perhaps you see a pattern starting to emerge here. Now let's take a look at another element. Let's try sodium. Here's sodium on the periodic table. And so it has 1 valence electron. It would really love to have 8. And so how is it going to obtain that octet? If it has 1, it would like to have 8. Well, some students look at that and say, well, maybe sodium is going to gain 7 electrons. Well, I guess that's possible, but let's look at its electron configuration. Now, what would happen if this 1 electron right here, that 3s electron, were to just kind of disappear and go away. How many valence electrons would it have left? Do you see that now the second energy level is the valence shell? And so we'd have 2 and 6, so 8. So it actually has an octet by doing that. Now, which do you think is easier? For sodium to gain 7 or to lose 1? Well, if you said lose 1, you're correct. And so sodium actually loses 1 electron. Now, if sodium loses a negative electron, then what's its charge going to be? Well, it's going to be positive. And so its charge will be +1. So we'll have an Na with a little plus written next to it right there. In fact, all of these elements here in group 1, they have 1 valence electron. They're all going to do exactly that. They're going to have a +1 charge. And let's look at the element right next to it, magnesium. Magnesium has 2 valence electrons. It would really like to have 8. So how is it going to obtain an octet? Could it gain 6? Well, maybe it could do something similar to sodium and just lose 2. That would be easier, wouldn't it? That's what it does. It loses 2 electrons. And so it's going to have a positive 2 charge. And it's going to have a symbol like this, Mg2+. Now, hopefully, you're able to see that there is a pattern here. And if we look at the ions, and by the way, ions are just atoms that have gained or lost electrons. That's just the general name for these. We can look at these ions and classify them into 2 groups. Can you think of 2 groups that we could classify these into? Well, the simplest way would be to have positive ions, those that have lost electrons, and negative ions, those that have gained electrons. So the positive ones might be ions like these right here. And all those that are positive are called cations. That's an important vocabulary word. All the ones that have a positive charge are cations. While all these that are negative, like F negative, O2 negative, and N3 negative, those negative charged ions, or negatively charged ions, are called anions. And so cations are positive, anions are negative. Now sometimes students remember that cations are positive by just looking at the word cation. And if you write it like this, you might notice that the word cation seems to have a plus sign kind of hidden in it right there. So maybe that can help you remember that cations are positive. Now, I hope that you can see the pattern in the periodic table here. We see that there are patterns in valence electrons. There are patterns in how these elements are going to obtain an octet. And we also have patterns in the charges that they take when they become ions. So let's try this example here. If we look at the pattern, we can see that group 1 ions have a +1 charge. Group 2 ions have a +2 charge. So we see a little pattern emerging. Group 13 ions have a +3 charge. See the pattern emerging? +1, +2, +3. Now, group 14 ions can go either way. Since they're kind of halfway between 0 and 8, they can either have a +4 or a -4 charge, depending upon what they're bonded with. Group 15, those are going to have a -3 charge. Group 16 will have a -2 charge. Group 17, the halogen ions, are going to have a -1 charge. Now, some students, just like I said earlier, sometimes like to write these charges on their personal copy of the periodic table. So above group 1, they put a +1. Above group 2, they put a +2. Above group 13, they put a +3. And so on and so forth. They put a +4, -4 here, and then a -3, -2, -1. So they're always able to remember which groups have which charges. It helps them to remember those if they write them on their periodic table. So let's practice a bit here. What's the symbol of this element's ion? We have arsenic. Do you remember what charge that one's going to have? Well, it's group 15. It's going to be -3. So when you write its symbol, it's going to be AS with that 3 negative. How about this element over here? What's the calcium ion's symbol going to be? Well, it's in group 2. Do you remember the charge that's going to have? It's a +2. So when you write its symbol, it's Ca with a 2+ next to it. How about Tl? What's the symbol of that element's ion? Well, it's in group 13, and so those generally have a +3 charge, don't they? And so our best guess would be that Tl is going to have a little 3+ right next to it. Now, how about this ion here, iodine? Do you remember its charge based upon the group it's in? All these in the halogen group will be -1. So we write I with a little negative sign next to it. That's its charge. Well, hopefully, by this point, you're able to see the patterns on the periodic table. Lots of patterns here. In fact, we've learned patterns for valence electrons, patterns for how these elements are going to obtain an octet, and also how they're going to be ionized.